Hello, good morning, everyone. Today we are presenting our work on selective activation spiking neural networks, or what we call SA-SNN, designed for continual learning. This work has been done by me, Priyansh, Onkar Shinde, and Prakhar. Our goal here is to explain how spiking neural networks can overcome catastrophic forgetting and learn continuously, inspired by basically biological brain mechanisms. For the motivation part, one of the major challenges in AI is catastrophic forgetting. When neural networks learn tasks one after another, they tend to overwrite old information. But real world intelligent systems like robots or autonomous agents must learn new things without forgetting the old ones. So, interestingly, biological brains deal with this extremely well. What we do is we selectively activate only specific neurons for specific experiences. We also use context gating and sparse activity to avoid overlap between memories. SA-SNN tries to mimic these biological principles only. Moving on, continual learning problem. In continual learning, tasks arrive sequentially. The key challenge is we do not have access to previous task data, but we still want the model to retain knowledge of earlier classes. Specifically, the setting used here is class incremental learning or class IL. This means that at any moment, the model must classify among all classes it has learned so far, not just the current task. So the network must simultaneously learn new information and protect the old one. Moving on, why spiking neural networks? SNN basically mimics how real neurons fire spikes. Their computations are sparse and event driven and making them naturally efficient. They also have temporal dynamics, meaning they carry a sense of time, which creates a kind of built in separation between tasks. So, unlike KNNs, weights in SNN update only when spike occur. This spike driven behavior makes them promising candidate for continual learning. The key ideas of SA-SNN. The core idea of SA-SNN is to introduce selective activation inspired by the biological brains. There are two mechanisms involved, and first one of them is trace based K winner take all, KWTA, like very weird name, but each neuron maintains a temporal trace of recent activity, and at every time step, only the top K most active neurons are allowed to fire. This forces sparsity and prevents all neurons from activating simultaneously. Basically, in normal neural network, what we take is we take 100 or 200 or maybe 300 or like 50 neurons per layer. In here, we take thousands of neurons, and like real brains, we don't want all of them to fire at once. We want sparsity. We want only a few of them, a very grouped version of them to be fired at every time step. First was KWTA, and second is variable firing thresholds. So neurons that fire too frequently automatically get a higher threshold, so that they do not fire that often. So they become harder to activate again. This prevents the same neuron from dominating all the tasks. Basically, some neurons that may fire every time. We don't want that. Together, these two mechanisms create separate subpopulations of neurons for different tasks, reducing interference and forgetting. Now comes the biological inspiration part. In the brain, there is a concept called context gating, where only specific groups of neurons activate for certain experiences. This gating prevents memories from overlapping. This SA-SNN mimics this through via temporal trace, which acts like a neural activity memory, and an adaptive thresholds, which ensure balanced neuron usage. This makes the model more biologically realistic and improves continual learning performances. Now we discuss about this SA-SNN architecture. Uh, the pipeline is very simple. Input embeddings goes to a hidden spiking layer, which goes to a linear classifier, and then we produce our results. The hidden layer is where all the selective activation happens. The hidden layer contains temporal trace updates, the KWTA maskings, variable thresholds, and IF or LIF spiking neuron dynamics. This modular design is what makes SASNN easy to implement and extend. Moving on, the temporal trace update part, like this temporal trace update, which is part of hidden layer, has been discussed here. So the temporal trace is like an online memory of the neuron activity. If a neuron fires recently, if a neuron was fired recently, its trace value is higher. This traces the news basically to decide which neuron gets selected in the top k. When we select these top k neurons at each time step, this trace is what we use for this selection. So the network remembers which neuron are active over time and uses that history to stabilize its behavior. Then comes this KWTA mechanism. So in each time step, the model selects only k neurons with the highest trace values. All other neurons stay silent. This means that each input only activates a small subset of neurons that we initially called subpopulation of neurons. So as tasks change, different subsets get activated. This creates somewhat task specific subnetwork or neuron subpopulation, which is the key to avoiding interference between tasks. Now comes this variable threshold part. So the firing threshold of each neuron increases depending on how much it has been used. So if a neuron is firing too much or too often, its threshold rises, making it harder to fire again. This encourages the neurons, especially the silent ones, to participate. This idea prevents a kind of neuron dominance and ensures a more balanced use of this entire network. The SA-SNN uses standard integrate and fire IF or leaky integrate and fire neurons, LIF neurons. The membrane potential integrates input over time, and when it exceeds the threshold, a spike is generated. So, unlike uh, normal or standard neural networks, the ANNs, which fire every time with some certain activation values, these striking neurons fire not always, but only when a certain threshold value has been met. So the basic spike mechanism remains unchanged in this IF neurons also. And what SASNN adds is the selective gating on top of these standard neuron equations. So from here, Onkar will carry on. Thank you so much. My name is Priyansh, and this has been my part.
Hello everyone, I'm Onkar Shinde. So moving forward for the training pipeline of our project, like here we have worked on the class incremental learning setup, like which means the model gets task one after the another, and each task contains of the two classes, where across all the data sets we have the five tasks. So essentially we have completely five cross two classes present inside it. Here the main our key point is like we do not give the network task labels, so which means like the model does not know which task is currently learning, and it must figure out like how to separate the task purely through the selective neuron activations, and which makes the problem harder but more realistic. So we are not giving the replay buffer as well for it, like we don't want any old samples to get stored and used as the memory for the previous tasks. The network must retain its earlier task only through its internal dynamics and the temporal trace and variable thresholds present inside it. Like to train the spiral neurons, we use the surrogate gradient method with the STBP for the training purposes, and like it this allows us for back propagation through the time because the spikes are non-differentiable. Finally, we apply the L2 normalization for the stabilizing inputs, like both on the input embeddings and on the weights. This comes for like this is we have demonstrated in the report how we are using, and the reason for behind is normalized inputs helps to stay the model like stable and avoid too many spikes inside it, which improves the task separation properties. Then moving forward for the dataset we have used, like we evaluated the SA-SSN model on the four popular databases present here for benchmarking. Like we have to split into the five tasks for the two classes each. Like firstly inside the MNIST dataset, which is the handwritten dataset. Here the performs like the model performs extremely best on it. Then the second model, like the second dataset is of the fashion MNIST dataset. where it is simple but more varied. Like instead of only the digits, there are the clothings like the shirt, shoes, bags, etc. If the model is stable inside it and having the high accuracy as well, then the next dataset is CFAR 10 dataset, which is having the natural images like the cars, dogs, birds, which makes the harder for the shallow networks. Here, like forgetting is moderate present here. Then the next dataset is SVHN dataset, where the street digits are present here. It is the most hardest one for the predicting it, like because here consists of the noise, colors, and the backgrounds. Now let us see the experimental setup which we have done here. Like we try to keep our model simple and lightweighted, just like the one hidden layer present inside it of the spiking neurons. Then the size of that hidden layer is 1000, and the trace decay for it is 10. Then only the 10 neuron fires at particular timestamp. Then the maximum threshold is kept as 2, and the control threshold growth rate is 20 to the power 6. We have here used the 16 time step, which helps to spikes the accumulate, and the batch size of 256, which is the standard SGD batch size, and 5 box per task. Here, like the SGD optimizer is used. So now moving to the results part, the feminine like fashion feminist dataset, which are used for training as the SNN, it shines like it is giving the better result for us, like the strong performance, which are indicating of the two things. Here the mainly results which are getting like the consistent strong result here is around 93 to 98% across the tasks for the all the five tasks. And then the like it performs the task separation extremely well. Like the network is able to route the different clothing categories into the different subset of the neurons. And like here, even though there is no for replay buffer or task levels are used, the earlier task remains stable on it. Then moving towards the CFAR 10 and SVHN dataset, there is a significant harder, and it's reflecting in the results. Like these datasets are already harder, like its accuracy hovers between the like 0.65 till the 0.75%, like it is around the 50 to 55% accuracy. And on SVHN the accuracy is slightly better in like intentionally, but settles around the 50 to 55%. Then but here is the important part is like the SNN still beats the vanilla SSNN baseline model. And like there is a noteworthy, it is a noteworthy because the model is very shallow and the encoder is very weak here. But we are running the 5 epochs per task. The images are complex and these are very noisy images present inside it. So like performance on this dataset is limited mainly because we are using the less depth model depth and short training we are doing it, and lack of the convolutionally encoders used here. With these limitations as well, like the selective activation mechanism manages to preserve the earlier task much better than the standard SSN1. Now for the combined results here, like the we put the dataset together and we observe the common trend present inside it. The actual accuracy was increasing from the task 1 to task 4 for, and like there is a slightly decrease in it from to for the task 5 for all the data sets present here. This pattern is like discussed in the original SSN paper as well, but and which is all our results are also demonstrating the same thing. Why it is happening is due to the model like gradually specializes the different neurons for the different tasks and improving the separation between them. But as the time reaches till the like task 5, the neurons has used many of its most expensive neurons, and the threshold growth makes it harder to adapt the further new ones which are coming from them. Therefore, overall, the trend clearly shows that the SSNN selective activation mechanism is more effective across like all the data sets present here. Now, from the this part, Prakhar will continue.
So, hi. Now I, Prakhar, will be explaining from here on. So now let's talk about why SA-SNN works so well. So everything we have shown so far, the stable FMNIST performance, the moderate but meaningful gains on CIFAR-10 and SVHN, all of that can be traced back to how SA-SNN uses selective activation biologically. There are four reasons why this method works. So first one is the sparse task specific activation. The network doesn't use all neurons for every input. It only activates the top k most relevant neurons, and k is as small as 10 in, let's say, 1,000 neurons. So every task ends up activating a different subpopulation. So this is extremely similar as to how our brain stores memories. That is, only a small group of neurons fires for any particular experience. The second one, that is the reduced overlap between tasks. So now if two tasks uses entirely separate neuron groups, then learning task B does not interfere with task A. So this is basically the core idea behind fighting catastrophic forgetting. The third point, that is the temporal trace, captures the recent activities. So now each neurons maintains a temporal trace, like a memory of how active it has been recently. So this trace determines whether the neuron gets into the top K for the next input or not. So tasks create a kind of activity fingerprint that the model naturally follows. This produces stable routing. Similar samples tend to use similar neurons. The fourth one, threshold growth prevents reuse of old neurons. So it may happen that some neurons may get too good at firing. And if those same neurons keep getting fired, then all tasks will start overlapping and interfere. But SA-SNN forces these neurons to take a break by increasing their firing threshold irreversibly. This encourages quiet neurons to activate and be useful. Together, these mechanisms produce a network that naturally separates tasks, preserves old knowledge, and remains extremely sparse and energy efficient, all without replay or task labels. So, this makes SSNN biologically intuitive and computationally strong. Now, coming to the limitations of SASNN. First one is the performance on complex data set could be improved. So, as we before that, even though the method works quite well, especially considering how simple the architecture is, there are some clear limitations that we observed during the experiments, which was also mentioned in the original paper. First one is the performance on complex dataset that could improve. So on CIFAR-10 and SVHN, we saw that the accuracy stays around 50 to 55%. This is still better than a vanilla SNN, but far from the state-of-the-art models. The reason is that our models uses no convolutional encoder, just a shallow linear embedding layer. So the model struggles with high complexity images. The second limitation is that the network uses only a single hidden layer. So this is great for testing the SA-SNN idea, but limiting for actual performance. Deep SNNs or multi-layer architectures would probably do much better. The third one is no online task detection. So the model does not detect when a new task appears. In real world continual learning, the task boundaries are not known. Here, task arrives sequentially, but the model just continues training. So adding task-free or online detection would be important. The fourth one, that is the training time can be high. So as we know that training time is slow for spiky models. So even though this model is small, spiking neural networks require simulation across multiple time steps and backpropagation through time, BPTT. So training takes longer compared to a standard ANN. So these limitations do not take away from the conceptual contribution, but they highlight what needs to be improved in the next version before SNN can be used on a large scale or real world application. Now coming to the future works. So let's talk about what can be done next. So based on these limitations, which we discussed in the previous slide, there are several promising directions for future work, both for our project and for general SA-SNN architecture. First one is the multi-layer or deeper SNNs. So adding more spiking layers would allow richer feature extraction. This is especially important for datasets like CIFAR-10 and SVHN that needs hierarchical patterns. A deeper network could dramatically improve results and reduce forgetting. The second one, that is the online or task-free continual learning. So right now the tasks are given in sequential order and in batches. But in real systems, robotics or sensor networks type, they never receive strict task boundaries. So extending SASNN to automatically detect task changes would make it more practical and relevant for the real world tasks. The third one, that is the neuromorphic hardware deployment. So before because SASNN is sparse and event driven, it is a perfect candidate for neuromorphic platforms like Intel Lohi and IBM True North. These chips naturally support spiking activities, and the selective activation can reduce energy even further. The fourth one, that is the better input encoders. So instead of using a shallow linear embedding, a small CNN front end or a biologically inspired retina encoder would significantly improve accuracy on complex images. So that was the better input encoders. Now the fifth possible future work could be the automated hyperparameter tuning. Parameters like k, comma and k, tau, and threshold growth rate p heavily influence how tasks get separated. Using hyperparameter search, Bayesian optimization, or evolutionary methods could find even better settings. Overall, there is a lot of potential for taking SA-SNN from conceptual demonstration to a high-performing continual learning system. Now, coming to the conclusion. So, finally, let me conclude on our whole work. So, in this project, we implemented and evaluated selective activation sp- selective activation spiking neural networks, or SSNN, for continual learning. So, and the key message is that the selective activation enables continual learning without replay and without task labels. This model uses two biologically motivated mechanism: the trace-based KWTA mechanism, which means the trace-based K winner take all, and the variable threshold, along with variable threshold. So this combination creates task-specific subnetworks inside the same model, and thus reducing the forgetting tendency. So also our as already shown that our experiments on four data set, that is the amnes fashion amnes CIFAR 10 and SVHN. It shows that SASNN performs extremely well on simple to moderate data sets. It maintains stable accuracy across tasks. Even on difficult data sets, it outperforms the standard spiking neural networks. And all of this is achieved without any replay buffer or task labels. This demonstrates the potential for energy efficient and brain inspired continual learning using spiking neural networks. So, overall, SASNN is a strong step towards realistic and scalable continual learning in spiking neural networks. So, I would like to thank you, and that's all from our side. And we'll be looking forward to hear more from you.